Like I was saying, you may have kind of seen this coming or have seen this before. AAHL2, we're going to be doing 5.3 to 5.7. So we're talking about derivatives, a word I think seems like everybody's heard before. You guys heard of derivatives before?
Yes. We did a little bit of practice last year.
Yeah, and we're probably going to be basically doing mostly just what you covered last year, maybe a little bit more. Derivatives is kind of one of those things where when you learn the limits with first principles, that really horrible long process from the quiz, you're basically just doing derivatives a horrible long way. And so teachers, I'm always a little hesitant to just call them derivatives right away, because if you know they're derivatives, you can just take the derivative, which is so much easier, or you get a kid who Googles derivatives and then all of a sudden. But the derivative is something we already have been working with. You know, it's that little thing with, it still has x's most likely, that helps you find the slope. So I'm not going to write all this down, but when we follow the first principle limits and find the function that we can use to find instantaneous rate of change, that thing is called the derivative, something I think we already know. Now, we could do a whole thing, I guess we will do. We'll do one last limits with first principles, and it's up to you. If you feel like you don't need to write this down in your notes, then you don't need to write it down. I'm gonna kind of fly through this pretty quick. We want to figure out the slope at some instantaneous place, so we can't use average rate of change. We need to use something fancy with limits where h is going towards 0. And so, let's do it. Let's do the limit of f of x as, I'll wake up still today, h goes to 0, and then we're going to plug in x plus h, all the x's first, so that would be h squared minus 3 x plus h plus 2. Then we're going to subtract just a plain old f of x squared minus 3x plus 2, and we're going to divide that by h. We need to do a little bit of simplifying, maybe more than a little bit. Again, we're going to get, FOIL that out, x squared plus 2xh plus h squared. It should be that minus 3x, it should be that minus 3h plus 2 minus x squared plus 3x minus 2. Hopefully, because we still need an h, all of that stuff coming from here is going to cancel out with pieces. So if we have a minus 2, that should be found a plus 2. Perfect. A plus 3 needs to find the opposite. A minus 3, make sure it's the x and the x that go. Then we have x squared. We see we have these things. We want to cross out one h and only one h. So that h with this one, and one of these, not both, and one of these. That way everybody loses one h. And now we also need the h to actually go to 0. So we have 2x plus h minus 3, but this h goes to 0. And so let's get that out of there. Make this a little closer. There we go. Now this thing is something that we could use to find slope, and this thing is the derivative. Are we cool with derivative and what that is, what that means? Okay, cool. Now, that is a long, long process, and it's annoying, and it takes too long, and finding derivatives of functions like this is possible, but what happens if we get something crazy, like if we have a rational function instead of just a polynomial? What if we have square roots? What if we have anything else more complicated? This is just going to become exponentially more difficult. So we're going to come up with many, many ways to find derivatives, and basically we're going to be learning shortcuts, and this you won't do for like another 3 months, which is nice. So the first shortcut we're going to learn, and honestly you likely already learned, is the power rule. A lot of times teachers will be like, calculus isn't hard, I could teach you calculus in 5 minutes. And basically they're just gonna teach you the power rule and how the power rule works. To get fancy, f of x is equal to ax to the power of n. That's why it's called the power rule, because we're talking about the power of n, basically exponents. Then f prime of x is equal to n ax n minus 1. And that's our power rule. And maybe the a's and n's are intimidating you a little bit, but it's really not all that bad. We're going to be basically taking the n and putting it in front there with the a and leaving behind an n minus 1. Now, the n and the a, do you think we're going to be adding those, multiplying those? What do you think?
Multiplying.
Of course, multiplying. The last thing I want to cover is this little apostrophe hash mark thing. That's how we denote the derivative of f. Other things you might see, if you have y equals, you might have y prime, or a little y apostrophe. And again, it's just the way you denote a derivative. There are some other fancier ways that we're going to get to next time, but for now, that's what we're working with. So let's see that in action, and we don't even need to see a new problem. We can just see our old problem, x cubed minus 3x plus 2. The derivative of that is 2x minus 3. And if you think about this one at a time, the x squared, we put the 2 in front, it became 2x, and we subtracted 1, it went from 2 down to 1, and then it should have just been 2x. When we look here, that's what we got. We have minus 3x. This kind of thing with the x is maybe a little bit weirder, but it's even easier. The 1 comes out front, it just stays negative 3, and then the 1 minus 1 becomes 0, and x power 0 just kind of goes away. And lastly, we have a 2, and because we don't have any x's on that 2, it doesn't really have any protection, and it just kind of disappears. The way I like to think about derivatives is they're kind of like degrading your function. It's kind of like decay almost, and your function kind of gets worn away every time you do a derivative. And the x's are kind of like how much protection the term has, because if you start with x squared and you take the derivative, you're going to go down to just 1x. We'll talk more about how that works. Because the 2 doesn't have any x's, the derivative is 0. Cool, we did that. I don't think we're even going to get an example there, because we're just going to throw the other next rule on top of that. Then we'll do a problem, I suppose. This is going to be the polynomial rule. So polynomials are just strings of functions. You could kind of think about them. So again, getting a little fancy, if f of x is equal to g of x plus h of x plus k of x, don't let that stress you out too much. We're just saying these pluses are kind of splitting up our different terms, that's all it is. Then f prime of x is equal to g prime of x plus h prime of x plus k prime of x. So if you've got a string of things in a row, you just take the derivative of them kind of separate. So those pluses are almost separating things completely. That's why when we went back up here, again, to the example we already did, we didn't have to take the derivative of this whole thing as one piece. We could just take it one term at a time. Obviously, for these super easy polynomials, there's no problem with that. We can just go one at a time. But sometimes you might see a really complicated function. Maybe it's something like 5e to the x minus sine x plus 12x cubed. And that sounds like a whole bunch of math, but you can just take it one thing at a time. Do the derivative of 5 e to the x, do the derivative of sine, do the derivative of whatever it is, and take them one at a time. You'll be alright. So this pretty much means as long as we have a function that looks like a polynomial, we can take the derivative using the power rule. So let's do one example and then we'll kind of move on. You only get one example today because frankly this isn't very hard and I think you already know a decent bit about it. J of x is equal to 5x cubed plus 3x squared plus 10x minus 1. Can you find J prime of x? Alright, there are 4 terms for this polynomial. We're going to start up front. Is that you got what this derivative here is?
Wait, do I say the entire thing or
Just the first term.
15x squared.
15 because the 3 comes out front, squared because the 3 degrades 1, subtracts 1. Great. Josh, you got the second term?
6x.
6x. Alex, you got the other one?
10.
We're done.
When it's finished.
That's it. Alright, is that negative 1? Gone with the wind. You see it forever. And there you go. There's our derivative. Awesome. Any issues with this? Any questions with this? Sweet. We should be able to do a quiz on that right now and get 100, to be honest. There's not much depth to it there. But we do not have a pop quiz today. Alright. Moving on, we're going to be talking about Q exponents, Q being the set Q, which is the rational numbers. Sometimes you'll see it written like that. You guys know like the all real numbers are, where they put like an extra line behind it. Yeah. This Q is basically the same thing. They just put like some of those extra bars on it to make it sturdier, more like a math thing. Do you guys know what rational numbers include? What is it?
It's like R.
Terminating numbers. Numbers that terminate. Like terminating decimals.
Right.
Or like they repeat in a pattern.
Right. Basically, numbers you should be able to put into a fraction. So this includes regular numbers, it includes 0, it includes negative numbers, it includes fraction numbers, which are numbers that terminate, numbers that you could, repeat. Sweet. So we're going to be talking about how do you deal with fraction exponents. Now this is a big thing because if we're doing the power rule, we know how to handle exponents. And so if we see weird exponents, we have to know what that stuff means. So the first one we want to look at is 1 divided by x squared. Ideally, we can use our power rule to handle this 1 over x squared. The issue is, what are we supposed to do? Is it different because the x squared is in the bottom? Does something work differently? The truth is, we want to rewrite this so that it is closer to our kind of standard form. We want to rewrite this so it looks more like ax power n. So, what can you do to rewrite x squared?
Negative x, or x to the negative 2.
Perfect. We can use negative exponents. So we can make it look like this. X to the power of negative 2. That's extremely key. We're going to be doing that very often. And that basically allows you to deal with a lot of weird fraction stuff. Turn it and use negative exponents. Now that it's in this case, we can do our power rule from here. Put the negative 2 out front, handle it like that. I do want to say that you can't ever finish a question with negative exponents still in there. So a lot of times it's rewrite it, take the derivative, rewrite it again, and kind of move all those negative exponents back to the bottom. Okay? And the other one we want to talk about is the square root of x. How can we rewrite that?
X is 1/2.
Right. X to the bottom number is the root, so because this is a square root, meaning 2, that's why the 2's down there. If it was a cube root, it would be the 1/3 power. And the top number is how many x's are in that root. Right now there's only one x in that root, but if it was something like this, that would just put a 3 on top. So we gotta know how to handle dealing with square roots, dealing with fractions. You okay with that? Okay, we'll do question here.
I have a question.
Yeah.
So you know how we have to rewrite the negative exponents back into like a fraction?
Mhm.
But do we have to do the same thing for the fractional exponents back into the root version of it?
Yeah,
Okay.
yeah. Otherwise, cause like, if you have like x cubed over, I don't know, x power 3/2, this is 3 x's inside of a square root, which is enough to bring an x outside the square root. So it could look like this, but if you don't do this, you might write it like this, which is just, I know, awful.
Yeah.
So, yeah. We're kind of in the point where we don't want to cut any corners. We want to like, really kind of flesh out our algebra. It's not really algebra, but make it look extra nice. Okay, let's do a question here. L of x is equal to 1 over 3x cubed minus 1 over 2x squared plus 1x. Same thing as before, we're trying to find the derivative. I'll give you guys some time. No, we're crushing it. We're almost done with those, to be honest. Alright, as you're finishing up, we didn't see in our example up here, make sure that when you are dealing with these x's in the bottom and you're moving them up to the top, it is only going to move the variables. We don't want to touch the constants or the coefficients that are in front of those variables. So if you brought up this x cubed as an x to the power of -3, the 3 should not have come with you. It should have been just the x that came up. So what we should have is something that looks like 1/3 x power -3. That's kind of our rewrite, and then we take the derivative of that, which brings the -3 out front, which conveniently is opposites with the 1/3, so we're going to get just a -1 out there. And then when we subtract 1 from an already -3, we're going to get -4. Kind of a lazy morning kind of mistake is you say, oh, -3 minus 1 is -2, but that's not, of course, how numbers work. So that first term, I have to rewrite it, is going to look something like -1 over x power 4. Anybody want to give me the second term? What do you got, Vidal?
1 over x to the third.
Yeah, we're going to have plus 1 over x cubed. Again, I should probably do this. That's because we rewrite it as -1/2 x and -2. Then the -2 comes out front. It's opposites with the 1/2 nicely, so we get x and then -2 minus, in other words, -3. That's why we did that. And you can probably see the pattern down here. We should have -1 over x squared. And then what happens with that 1/2? Gone forever. It's just a constant. It doesn't have the protection it needs to survive the apocalypse. Okay with that? Okay. Up next, the last thing. Let's do this. Leave a little bit of room after L prime. Leave a little bit of a gap. We're gonna talk about the very last thing for the day, which is second derivatives. And beyond. Ooh. Tough handwriting. A little bit better. Alright, as basic as it gets, x power 5 plus x power 4 plus x power 3 plus x power 2 plus x plus 1. Sometimes you'll hear say take the derivative, sometimes they'll say find the first derivative, which just means do the derivative. So, Josh, you're in charge of the whole thing. What's the whole derivative here?
5x to the 4th.
Yep.
4x to the 3rd.
Yep.
3x to the 3x squared.
Mm-hmm.
Plus x
Plus what?
plus x. Wait, no, plus 2x.
Yep.
Plus 1.
Yep.
And then 0.
Right. Sweet, so this is our first derivative. Again, I like to think about it like there's like a nuclear, and we just like are degrading and disintegrating, and our function is just kind of withering away. As we take our derivative, the constants get wiped out. We all degrade down in x value, which is kind of weird if we're starting off with those negative exponents like we saw in the last problem. But for normal exponents, they're just going down. Sweet. The second derivative and beyond is just go again. Take another derivative. I guess I should have written that little hash mark there, sorry. We will denote that with a second hash mark, which is okay, sweet, of course that's what we would do. And then we just take the derivative again. Alec, you're in charge of this one.
20x to the 3rd plus 12x squared plus 6x plus 2.
Right. Everything degrades away, the coefficients are getting bigger, but now, let's say I wanted to find the 10th derivative of this function. How much work would that take?
It would take a lot.
Or,
Does it take exist? If does it exist? Or would it exist?
No.
Can you go that?
so let's debate what you mean by does it exist.
It would just be f x equals
Well,
0.
it would, well, if it's x to the 5th in the original equation, there's not gonna be like a slope by the time you get to like that many derivatives, right?
Right. You only have a couple layers of protection to survive these derivatives. If we take the 10th derivative, the 100th derivative, eventually all of these are going to wither away to the value of 0. I would disagree that it won't exist, because I mean it's still 0, it's still a number of something. But right, eventually this just is going to keep degrading and we'll get all the way to 0. So just for the sake of it, we're going to do that. We're going to see how long does it take to get to 0, which is also pretty predictable. The third derivative is 3 little hash marks. That's going to be 60x squared plus 24x plus 6. That one's going to go away. at some point we gotta quit with the little hash marks. The 10th derivative isn't gonna be 10 hash marks. So once we get to 4, just like on Roman numerals, you switch it up. You don't use Roman numerals, you just use a 4 there. So similar to Roman numerals, that is where the back breaks and you switch it up, but you just go to nice boring little numbers there. So the 4th derivative is going to be 120x plus 24, and this is getting easier, not harder. The 5th derivative is going to be just 120, and our 6th derivative is when we bottom out. We hit 0, and at this point, we can keep taking derivatives, but we're just a barren salt flat. There's nothing going on, we've been nuked to death. Now,
Oh, yeah.
yeah,
So is there like a quick way to find a specific derivative, like without having to go through having to find the previous ones?
that is not really a thing that you ever need to do.
Okay.
So the reality is, we don't need to find a shortcut like this.
Okay.
But if you wanted to find the shortcut like this, you know, if you just had some sort of term, let's say it was 5x to the power of 6, and you wanted to take like the 4th derivative of it, you could, I guess, again, this is unnecessary, but you could say the first puts a 6 in front, and the second would put a 5 in front, and the third would put a 4 in front, and the, you know what I'm saying, and the 4th would, and then you could say, this up here is good. But again, you don't ever really need to do that.
Alright.
To be honest, the multiple derivatives thing is more so just a show of we could do it, and in a while we'll talk about a niche case for the 2nd derivative. But like the 3rd and 4th, we'll leave that for the big guys in college. Now, our function, absolute barren wasteland after 6 derivatives. Are there any other functions that could survive longer? Of course, if you have anything with a bigger x power, are there any functions that could last forever? They have perfect nuke immunity, or they have nuke kind of protection or something like that. In order to do this, we have to leave polynomials behind, because these nice boring powers, where we have nice boring numbers, they eventually, you know, degrade. We already saw with the L of x. Whoa, where'd we go? Here we go. L of x. I'm pretty sure L of x is gonna start getting really ugly, but I'm pretty sure it will last forever, because we went from 3x's on the bottom to 4x's on the bottom, and up next is gonna be 5x's on the bottom. So after 100 derivatives, we're still gonna be around. So there are, of course, functions that are still around. And what we're gonna do now is talk about an interesting one, which is sine of x. What do we think? Do we like trig? We like sine, cosine, tangent? A little bit, not so much. Okay. Well, I'm gonna hurt your brain here. Maybe. You guys are smart kids, I forget sometimes, but. Do we remember that?
Yes.
That's the function of sine. And we haven't done a whole lot of this, but let's talk about what the derivative means, right? The derivative is the instantaneous rate of change, which means g prime should be some sort of function that models all the different slopes of sine. And the derivatives have graphs too. Sometimes you'll be shown graphs or asked to make graphs. Maybe you don't get this part at all, and all you get is a curve like that. And you need to look at that curve and identify, okay, the slope here and the slope there, and you can build the derivative from that. So, if we look at this, this is sine, here's 2 pi, here's 1 pi, here's half a pi, here's 3 halves of a pi. Are there any places on this graph of sine that have notable slopes?
So half a pi
Yeah.
and 2 or 3 pi over 2 have 0 slopes.
Excellent, right? We're talking about slopes. We can visualize instantaneous slopes with tangent lines, and the tangent line is looking nice and flat right there. And the tangent line is looking nice and flat right there. So that is a 0 slope, 0 tangent line at pi halves and 3 pi halves. So that means that this is G, and this is G prime. Our G prime should have, this is the graph of those slopes. The slope is 0, so on G, the value is 0. Same thing here, okay? Now the rest of these slopes of G, it's a curve, so it's changing all the time. And I don't know about exact numbers. 0 is a great call. But I could definitely think about the general, like, is it a positive slope or a decreasing slope? Is it going up or is it going down? So, we know it's 0 right here. Oh, we know it's 0 right here and 0 right here. Before the first 0, before we get to pi halves, before we get to the maximum, is it going up or down? It's going up. And that means that the slope is positive or negative? Positive, of course. And since this is the graph of the slopes, we have to be up here in the positive side. So before we get to this dot, which is the maximum, we should be on the positive side, which means we're actually going to be up here, looking something like that. And what about at the very, very end? We're increasing again.
The same.
So it should look very similar, because at the very, very end, we're increasing. In the middle of those two terms, we're decreasing, right? And this is where, I'm not sure if we'll fully grasp this all the way, because we haven't done sketching here. I'm just kind of giving you a taste of this. Where between these 2 points is it steepest going downhill? At pi. So that means on G prime, the steepest downhill is the most negative slope, which means our slope should be deepest down here at pi. And there we go. So that is us analyzing the sine graph, looking at its slopes, and then with a little bit of help with me, just kind of throwing together G prime. What is that?
Cosine.
Cosine. And so, beautifully, the derivative sine is cosine. Wow, how nice. Well, let's go for it again, because hopefully, we'll take another derivative. We're gonna be right back to sine. So let's see how it works. This can be G double prime, pi 3/4 pi 2 pi. Where does this graph have zeros? So the instantaneous rate of change is 0. At the peak, at the valley, at the peak. Here, here, here. Is this on the right track? Yeah, this is looking kind of siney, to be honest. Okay, so that means we're talking about this place, and this place. As we go from 0, or the exposition of 0, to the exposition of pi, are we decreasing or increasing? Decreasing. Since this is the slope, we're not allowed to go up to the positive side, because that's the increasing side. We have to be down here. And so, did we get back to sine? No. It's not sine. Those don't match. That is negative sine. Very important. Now, I totally could have just told you in 2 seconds, sine makes cosine, and cosine makes negative sine. But we have tons of time in class, and I think this is a reasonable introduction to looking at this graphs and derivatives. What do you think comes after the derivative negative sign.
Negative cosine.
Right, and that we should know because we know that sine derives into cosine, and this -1 is just a coefficient, and those coefficients, they don't change. It's like the little a there. Nothing really happens with it. So G3, G third derivative would be negative cosine of x. And what is negative cosine of x gonna get you back to?
Sinus.
Finally. So these derivatives would last an eternity. They would be in a little bit of a cycle. Does this remind you of anything else in math that does this little cycle on a little 4-turn loop?
Imaginary numbers.
You know what
Oh, yeah,
about
like negatives and wait.
imaginary numbers?
Yeah,
Sure.
yeah, but it's
The exponents
of negative.
of the little I for imaginary numbers, right? Because if you kind of have 1, then it's just 1. If you have I squared, it's -1. And then if you have I cubed, well, now it's an I and a -1, so now it's -I. And then if you have 4 of them, you're gonna loop all the way back around to where you started. So that is kind of similar. It's not really related in any way, but it kind of might connect 2 parts of your brain that can work together. The only other thing I have on here is that we could go back and do a second derivative of L,
Sure.
which would be a little bit of work with those fractions. But at the same time, I'm feeling pretty confident. I feel like you guys are feeling pretty good. I guess you guys can look at that maybe, the second derivative of L. That's gonna conclude notes for the day.